Ladies and gentlemen, welcome again, probably to the last part of this chapter from the inner product spaces. In this lecture, we will talk about the orthonormal basis, and the most important thing here will be the Gram-Schmidt orthogonality procedure. We will show that a set of vectors is orthogonal and it will form a orthonormal basis, and we would like to represent this a vector relative to an orthonormal basis, and of course we would like to apply the Gram-Schmidt orthonormalization procedure. Okay, let's get started. Well, we will start with the orthonormal and orthogonal sets first, okay? So the first thing we want to talk about is orthogonal and orthonormal sets. Okay, well, we have seen in previous lectures, I think that was in, I don't know, in the vector spaces, yeah, in the vector spaces lectures, I don't know, one of the lectures, we have seen that the vector space can have many different bases, right? Well, for example, in R3, so we have seen that in previous lectures, that a vector space can have many different bases. Right? And now, for example, let's consider R3. R3, the three-dimensional space, has the basis, and I will write here the standard basis. Let's call this B, and it will be formed by these vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. So this is the standard basis. Right? For R3. Okay. And one important thing about these vectors, let's denote this by E1, this is E2, and this is E3. And there is one observation that is crucial here, is the following. The vectors from this basis, E1, E2, E3, are mutually orthogonal What does this mean? Basically, this means that if you look at the dot product between them, let me do it in this way. E1 dot E2, well, this is 1, 0, 0 dot 0, 1, 0. Well, clearly this will give you 0, and then similarly, E2 dot E3 will be 0, and E3 dot E1 again will be 0. As you can see, this is what it means for these three vectors to be mutually orthogonal, these E1, E2, and E3. But there is also a second important characteristic for these three vectors, is that each vector from the basis B. In other words, each vector E1, E2, E3 is a unit vector. Again, another important thing. Well, it's quite clear if you look at the length of each one of them, and I'll leave it to you as an exercise to see it. This clearly is 1. Well, this is a standard basis in R3. Of course, everything can be generalized for vectors in Rn, no problem with that. But, well, we would like to, the main advantage of working with these vectors is that we will, this will be very useful when we'll deal with the Gram-Schmidt orthonormalization procedure. These unit and mutually orthogonal vectors will be important for that purpose, and we'll get there. But before that, let's state the definition. Definitions. Okay, there will be 2 definitions here. Now, this will involve for orthogonal and orthonormal sets. Okay, we have the following definition. A set S of vectors in an inner product space V right? Is orthogonal when every pair, let's say it like this, every pair of vectors in S is orthogonal, right? If, in addition, each vector in the set is a unit vector, then S is what we call orthonormal. Okay, so that's basically the 2 definitions. Orthogonal means that they're mutually, their inner product is 0, right? They're perpendicular basically, and orthonormal, this means that they're unit vectors. And let me just state it. So for S, let's suppose we have S, which will consist of these vectors, V1, V2, Vn. The above definition has the following form. Okay. Let me state it like this. Orthogonal means, and here I put orthonormal. Okay. Orthogonal means that the inner product between Vi and Vj is 0 for all I different than j, right? That's the condition for orthogonality. And orthonormal means the following, two conditions. Again, the first one is the same. The inner product between Vi and Vj is 0 for all I different than j. As you can see, this is the same condition as for orthogonality, but there is one extra condition, and that is that the length of Vi is 1 for all I from 1 to n. So each vector has length 1, and this is what it means for a vector, for a set S to be orthonormal. So they need to satisfy those two conditions, as you can see. Well, as you have seen, this basis here, S, right? The standard basis for R3, clearly this is a orthonormal set, right? Okay. Well, let me point out a remark here. If this set S, if S is a basis, then it is an orthogonal basis or an orthonormal basis or an orthonormal basis, right? Okay. Like I said, the standard basis for Rn is orthonormal, right? It's just, you just mimic the same procedure as we described for the standard basis in R3. For example, let me give you another example. So let's pick another example. Let's say example 1. Something that is not obvious. Well, I would say a non-standard orthonormal basis, and we'll pick this in R3, for R3, let's say. Okay? Let me see the example. Show that the set, and let's call this set the following. S will consist of these three vectors, let's say v1, v2, v3, and this will be v1, let's say, is 1 over square root of 2, 1 over square root of 2, and let's pick 0. Then the next one will be negative square root of 2 over 6, square root of 2 over 6, and the last one is 2 square root of 2 over 3. That's v2, and v3 will be 2 over 3, negative 2 over 3, and 1 over 3. Okay, we have these sets. Show that this set is an orthonormal basis for R3. This is important. Well, it's quite clear what to do. we have to show two things. Let's look back. As you can see, for orthonormal, if I want this set S of these vectors, V1, V2, V3 in our case, to be an orthonormal set, I need to show that they're mutually orthogonal, and I have to show that they're unit vectors. If I show these two things, then S is an orthonormal basis for R3. First, let's show that V1, V2, and V3 are, are mutually orthogonal. Okay, in this case, we need to compute the dot product of V1 and V2. Since we're in R3, we can call this a dot product of, and we also have to compute the dot product between V2 and V3 and V3 and V1. In this case, we have to dot these two vectors. Okay, and when we dot this, guess what are we going to obtain? This will be negative 1/6 plus 1/6 plus 0, and this will be 0. Okay, great. Now let's look at V2, V3. This will be negative square root of 2 over 6, square root of 2 over 6, 2 square root of 2 over 3, dot, negative square root of 2 over 6. Okay, again, here, if we do the computations, this will give us negative square root of 2 over 9 plus, minus, minus negative square root of 2 over 9 plus 2 square root of 2 over 9. And guess what? This will give us 0. And now the last one will be V3, V1, right? V3 dot V1. And we will have so this will be 2 over 3 square root of 2 minus 2 over 3 square root of 2 plus 0, and this will give us again 0. Therefore, the three vectors are mutually orthogonal, and now the second part is to show that V1, V2, and V3 are unit vectors. All right, let's do this. So to show that these are unit vectors, we need to show that V1, the length of V1 is the same as the length of V2 and is the same as the length of V3, and all three of them are equal to 1. All right, let's look at the first one. The length of V1 is nothing else than just the square root of V1 dot V1. And this will be the square root of, let's see, 1 over 2 plus 1 over 2 plus 0, which is 1. The square root of 1, which is 1. Now the length of V2 will be the square root of V2 dot V2, which will be, let's see, 1 over 18 plus 1 over 18 plus 8 over 9. And if you do the computations, this again will give us 1. And the last one is the length of V3, which is V3 dot V3, the square root of this. And this again will be V3 4 over 9 plus 4 over 9 plus 1 over 9, which again will be 1. Therefore, this implies that S is an orthonormal set, which is exactly what we wanted to prove, right? Okay, so this was pretty straightforward. As you can see, these three vectors, if we want to represent them geometrically, they do not lie in the same plane. That's the funny story about these three vectors. All right, right? Okay, now let's talk about another orthogonal set, and this is, again, I'll have to go back to calculus. It will be very hard for me to avoid when I talk about orthonormalization and all this kind of stuff. It will be very hard for me to avoid talking about integral calculus. So the second example, example 2. And let me remind you that last time I talked about the space of continuous functions, right? The vector space of continuous functions, real values, continuous functions defined on a closed and bounded interval. And now, well, we've worked through examples with C01, right? The space of all continuous functions, real valued continuous functions defined on the closed interval 0, 1. And now what we're going to do is the following. We'll define in this space of 0, 2 pi. Again, this is the space of all continuous functions defined on the closed interval 0, 2 pi, real valued, which are continuous. We define this inner product and as you're used, the inner product between f and g will be nothing else than the integral from 0 to 2 pi of f of x times g of x dx, right? Here, we want to show with this, show that the set, and here is a very interesting fact, because this set is very important when you come. It will be very important in PDEs when you will talk about the Fourier series, when you want to see the Fourier series of a solution. I don't know, to the heat equation or whatever, wave equation. And this orthonormal set pops out many times there. So this set will be, let me write it with a different color. I want to emphasize that. This set S will be 1 sine of x, cosine of x, sine of 2x, cosine of 2x, and we'll keep going, sine of nx, cosine of nx. Guess what? This is orthogonal. I'm not talking about being an orthonormal, not yet, and you will see why. Maybe this is not an orthonormal, but there will be a procedure to make it look like an orthonormal. So I want you to look at it. Right? So it's basically the trigonometric functions sine and cosine. let's see. Okay, what do we need to show? We need to show that these two are mutually orthogonal. Well, to show that the set S is orthogonal, okay? Well, we need to verify the inner product, right? We need to verify the following inner products. And you'll see immediately what I mean by that. Okay, first let's see, one with sine of nx. This, by the definition, will be the integral from 0 to 2 pi of sine of nx. And sine of nx dx is to 0. Then the same thing happens with the cosine. Right? And now, let's look at when we have the inner product between sine of mx and, okay, let me write like this. Sine of mx and the sine of nx. The inner product between these two, so this will be the integral from 0 to 2 pi of sine of mx times cosine of nx dx. Well, let's see. What is the value of this? Well, the value of this will be 0, again. So quite easy to see. And now, if we compute the inner product between any two sines and cosines, sine of mx and sine of nx, wait, what am I, no, here I put cosine, I'm sorry. And here's sine of nx. This will be nothing else than just the integral from 0 to 2 pi of sine of mx times sine of nx dx. Guess what? This will be 0 as long as, or m different than n. And the same thing will happen with the cosine. Cosine of mx, cosine of nx, again, this is 0 for m different than n. Okay. Right, so we have this. Now the question is, what happens when n equals m? And in fact, let's prove one of these. Let's look at, for example, the sine and cosine. So for example, so how do we prove this? Yeah, the first one. So let's take the first one. So the question is, how do we show this? Because it's not obvious. Well, it kind of requires a little bit of trigonometry. And let's look at it. The inner product, so sine of mx cosine of nx, which is the integral from 0 to 2 pi of sine of mx cosine of nx dx. So we want to prove that this is 0. So let's see. This guy, and I'm going to use here, I'm going to write it in this way, and then I'm going to tell you what I used. This is 1/2 the integral from 0 to 2 pi. And what I'm going to do is will be the following, will be sine of m plus n x plus sine of m minus n times x, right, dx. And again, I express this as this, this will be the sum of two integrals, then this will give me 0. So basically, I just use the identity, the trigonometric identity, sine of the product between sine and cosine is nothing else than just the sum of these two sines. Basically, it's just the only thing you need to know is the trigonometric formulas for sine of a plus b and sine of a minus b. Anyway, I'm not getting into any details. And now if m equals n, we have that that the integral from 0 to 2 pi of sine of nx times cosine of nx dx. So we have that this guy, well, is nothing else. If you want to keep in mind that we have this formula. Okay, here I'm going to write it. Sine of 2a is 2 sine of a cosine of a. So we would like to write this. But in any case, in fact, we don't even need this. Why am I saying, what am I talking about? I don't even need this because this will be nothing else there than this will be just the, okay, it will be 1/2n sine squared of nx, right? Yes. And this will be from 0 to 2 pi. And guess what? After some computations, this will give you 0. Well, the set S is orthogonal, but now the question is, which is exactly what we wanted to prove, but the question is it orthonormal? Unfortunately, the set is not orthonormal, but not orthonormal. Well, it's quite clear why. If you look at, let's take only the vector 1, right? And if we square it, this is the integral from 0 to 2 pi of 1 squared dx, which is 2 pi. So this is not 1. So more also, if you look at, let's say, the length of sine of nx squared, this will be the integral from 0 to 2 pi of sine squared of nx dx, and this will give you pi. Or if you want to look at the length of cosine of nx squared, this will be the integral from 0 to 2 pi of cosine squared of nx dx, which is again pi. Definitely, these are not these are not unit vectors, right? But is there a way for us to make them look like unit vectors? Sure. I can divide by this quantity here for my vector 1. The same, I can do the same thing for the other two vectors. And guess what? It will follow that, it follows that the set, and I'm going to write it in this way. I'm going to orthonormalize it as let me denote this set by S prime. So I'm going to divide the first one is 1 over 2 pi. The second one will be 1 over, 1 over square root of 2 pi because I squared it there. 1 over square root of pi times sine of x. 1 over square root of pi times cosine of x. And I keep going. And I have 1 over square root of pi sine of nx. And 1 over square root of pi times cosine of nx. This guy is orthonormal. Okay, that's beautiful. So you see, I just divide by this constant 2 pi, the square root of 2 pi, in fact, because we squared it. And I can orthonormalize this basis. Okay. Keep in mind this exercise. It's very important, especially in the context of PDs and so on. Now I'm going to talk about the following. I'm going to talk about a very important theorem, because we have seen in these examples, in all these examples, we have seen that each set is linearly independent, right? And we have the following theorem. Theorem, I don't know the number, 1, let's say. Basically, this theorem says that orthogonal sets are linearly independent. So let's state it. If S will consist of these vectors, v1, v2, vn, okay, if S will consist of these vectors, okay, is an orthogonal set of non-zero vectors, this is very important, in an inner product space V, then S is linearly independent. Just like we said at the beginning, orthogonal sets are linearly independent. Okay. I'm not going to prove this. I would like to skip it, since I want to focus more on examples. And we have here the following corollary. Let's say corollary 2, whatever. If V is an inner product space, of dimension n, then any orthogonal set of n non-zero vectors, is a basis for V. This is important. Anyway, this follows immediately. And now we want to use orthogonality to test for a basis. And now let's see another example. I think this is example number 3. Okay. And now let me consider the following. Show that the set S given by, now let's look at the set. I'm going to consider the vectors in R4, and the first one is 2, 3, 2, negative 2. So this is my first vector. The second one is 1, 0, 0, 1. The third vector will be negative 1, 0, 2, 1, right? And the fourth one will be negative 1, 2, negative 1, 1. Okay, these are the 4 vectors. So let's say this is V1, this is V2, this is V3, and this is V4. Okay, so I want to show that this set is a basis for R4. Well, we have seen this before, right? Right, we have shown that this is a basis. When we did the well in the previous chapter, not previous, in the vector spaces chapter. Anyway, we've shown this many times, but now let's use a corollary. We want to use this corollary to show, to give even a simpler solution using. So let's look at the corollary. If I have an inner product space of dimension n, then any orthogonal set of non-zero and vectors is a basis for V. Wow. So basically, we have to show that this set is orthogonal. We only need to show that the set S is an orthogonal set. Okay, and now guess what? We're going to compute the dot product between these vectors. We're going to take them 2 by 2. Wow, there's a lot of things to compute here. So it will be 2, 3, 2, negative 2, dot with 1, 0, 0, 1. Oh my. This will give us 2 plus 0 plus 0 minus 2, which is 0. Well, of course, all of them must V. Okay, let me do it like this. V1, V3. And again, this will be 2, 3, 2, negative 2, dot with negative 1, 0, 2, 1. And this will give us negative 2 plus 0 plus 4 minus 2, which is 0. And now V1 dot V4, which will be 2, 3, 2, negative 2, dot with negative 1, 2, negative 1, 1. And this will be negative 2 plus 6 minus 2 minus 2, which will give us 0. Okay, now let's look at V2 dot V3, which is 1, 0, 0, 1, dot with negative 1, 0, 2, 1. Okay, which will give us negative 1 plus 0 plus 0 plus 1, which is 0. Okay, now if v2 dot v4, which is 1, 0, 0, 1 dot negative 1, 2, negative 1, 1. And this will be negative 1 plus 0 plus 0 plus 1, which will give us 0. And finally, the last one will be v3 dot v4, which will be negative 1, 0, 2, 1 dot negative 1, 2, negative 1, 1. And this will be 1 plus 0 minus 2 plus 1, which will be 0. Okay. Phew. Great. Thus, S is orthogonal, is an orthogonal set. And by the corollary, by corollary 2, it follows that S is a basis for R4. Wow, that's another way to show that a set of vectors is a basis for a vector space. That's very nice. Okay, well, we're getting closer to the Gram-Schmidt orthonormalization procedure, and you will see this will be the best part of this. Okay. Now, I'm gonna go back a bit to the representing coordinates relative to an orthonormal basis. And what I want to do now is the following. Okay, we have the following theorem. Say theorem 3, which will concern the coordinates relative to an orthonormal basis. And it says the following: if B, which consists of these vectors, v1, v2, vn, is an orthonormal basis for an inner product space V, then the coordinate representation of a vector, let's say W, right? Relative to B is the following, and I'm going to, is W will be the inner product between W and V1, V1 plus the inner product WV2, V2 plus WVN, Vn. Okay. Well, and here I want to point out a remark. In this theorem, again, this is very important. In the above theorem, well, if you look at these coefficients, right, they actually are very important. The coordinates, let me phrase it in the following way. The coordinates of W to the orthonormal basis B are called the Fourier coefficients, are called the Fourier coefficients of W. This name Fourier comes from Jean-Baptiste Fourier, was a French mathematician. Well, he made an extraordinary discovery back in the days, more than 200 years ago, and now which belongs to him, well, which is called these days the Fourier Series. And the Fourier series are basically important in everything. Even the phones, the signal that it sends today, it's based on the on Fourier series. Anyway, the corresponding coordinate matrix of W relative to the basis B is given by the following, and let's write it. This will be C1, C2, Cn will be transpose of this, which will be this matrix. And this is actually called the Gram matrix, but anyway. It's WV, or the inner product between WV1, WV2, and, in fact, no, let me write it. Which will be equal to this inner product transpose. Okay, so that's the corresponding coordinate matrix of a W relative to the basis B. Okay, and now let's see an example. Example number 4, I think. We want to find the corresponding coordinate matrix of a vector relative to a basis. So find the coordinate matrix of the following vector. Let's say W will be, let's pick a vector in R3, 5, a -5, and 2. Okay. Relative to the orthonormal basis B for R3 below. And we're going to want to pick the following basis. And let's be careful here. So we want to pick the following basis. 3/5, 4/5, 0. Okay, will be my first vector. Let's say, okay, Anyway, we'll denote them afterwards. The second one will be negative 4 over 5, 3 over 5, 0, right? Yes. And the last one, that's 0, 0. We can make things simpler. Okay, this is the first one. Let's call this V1. This is the vector V2, and this is the vector V3. Well, let's look at it. In fact, as you can see, what we need to do, we want to use the above theorem, right? Look at it. We want to use theorem 3. So I know that I have an orthonormal basis of vectors. In my case, I have the V1, V2, and V3. And we have for an inner product space, V, which in our case is the entire R3. And now we want to write the coordinate representation of a vector W relative to this basis. Well, we have the exact formula, and these are the Fourier coefficients of W. In fact, well, we just need to apply it. And what we need to do is we need to find the coordinates. Okay. And we have W dot P1. We need to dot W with each vector from the basis. In other words, we need to find a dot product between W and V1, V2, and V3. All right, in this case, we have 5, negative 5, 2, dot 3 over 5, 4 over 5, and 0, which will give us 3, which will give us negative 1. The second one, W dot V2, which will give us negative 7. And the last one, W dot V3. Okay, this is simple. This is 2. Okay, great. So the coordinate matrix the coordinate matrix of W relative to the basis B is given by the following. So we have the above formula here, right? So it's negative 1, negative 7, and 2, and this transpose, and that's it. Right? Anyway, it was pretty standard, right? So the only thing we need to apply was just the theorem, basically. Okay, now we're in the position, well, to talk about the Gram-Schmidt orthonormalization procedure. And you will see that this will be very, very useful and important. In other words, this is the most important thing that we will study in this chapter. Let me give you some history. Well, you have seen, but before that, let me give you a motivation for this. Well, we have seen that that working with orthonormal basis has its advantages, right? But now we would like to see a procedure that will produce such a basis of orthonormal vectors. And this procedure will be called the Gram-Schmidt orthonormalization procedure. And this is due to, let me mention, Jürgen Gram, German, both of them are German mathematician. And the second one is Ernhard Schmidt. Okay, and it has 3 steps. Okay, and let's write them. The first one is begin. We'll begin with the basis, begin with a basis for the inner product space. Okay. And here I'd like to make a comment. We don't necessarily need to that basis to consist of vectors which are orthogonal or unit vectors. Okay, let's mention this. It need not be orthogonal nor consist of unit vectors. Right? Now the second one is to convert the basis. So we start with this basis. Let me convert the basis to an orthogonal basis. We need to convert this. Okay, this is the second step. And now guess what? The third step, once we have this orthogonal basis, we would like to normalize it. So normalize each vector in the orthogonal basis. To form an orthonormal basis. These are the basic 3 steps. And now let's describe it in detail. We have the following theorem. Theorem number 4, whatever. Yeah, number 4. So let's describe this the Gram-Schmidt orthonormalization procedure in detail. Let B, let's consider a basis of this vector, which consists of these vectors, v1, v2, vn, be a basis for an inner product space V. All right, now let us consider another basis, which will consist of these vectors. Let's call them W1, W2, Wn, and now we will see how we obtain these vectors W1, W2, Wn from the initial, from the vectors V1, V2, Vn, where these vectors Wi's will be obtained in the following way. The first one, W1, will be the same as V1, and now we're trying to form an orthogonal basis, and we'll do it in the following way. W2 will be V2 minus, and we're going to do it, this will be the inner product between V2 and W1 over W2 and W1, right? W1. And now we're going to do the same thing for W3. We'll continue. This will be V3 minus V3 W1 over here I made a mistake, I think. This is W1 here. Yeah, otherwise I don't think they're orthogonal. Yes. Yeah, I divide by the. And here I'll have W1, the inner product between W1 and W1, and minus now V3 W2 over W2 times W2. And now we'll keep going. So we'll continue this procedure. It's quite clear what's going on at this point. And we're going to write the last one, Wn. We're going to write them in terms of the others, will be Vn minus two right? Minus, and we keep going, right? All the way to the last one, so minus the inner product between Vn and Wn minus 1 over the inner product between Wn minus 1 and Wn minus 1, Wn minus 1. Okay, and this way, this is the great idea of Gram and Schmidt, then, and in this way we obtain an orthogonal basis, then B prime is an orthogonal basis for V. And now okay, let me call this step 1, step 2, and now step 3. We have this orthonormal basis. We're trying to normalize it. And now we'll consider the following vectors. Let me consider Ui to be, since they're orthogonal, to normalize them is quite easy. We'll divide the vectors by their length. And guess what? Once we do this, it follows that then this basis, let's say B second prime, which will consist of U1 of these vectors, U1, U2, Un, is an orthonormal basis for B. Okay, is an orthonormal basis for B. also, we would like to say that the span of vectors v1, v2, vn is the same as the span of u1, u2, un. uk, okay, doesn't really matter here. For k going from 1 to n. Okay, this is written in details, the Gram-Schmidt procedure. And now I would like to, as you can see here, we have seen this kind of expression. We'll see, right, when we talked about the projection of a vector onto another vector. Anyway, so they look kind of similar. Now let's see some examples. How to apply the Gram-Schmidt orthonormalization procedure. And we'll see a couple of examples, and then I think we'll stop. But anyway, let's see example number 5, I think. I don't even know the example number 5. Anyway, example 5. Let's consider something very simple. Apply the Gram-Schmidt orthonormalization procedure to the basis B for R2. And this basis B is given by, I'm going to consider something very simple, of two vectors, 1, 1, and 1, 0, and 0, 1, let's say. It's actually simple. Okay. This is my vector V1, and this is my vector V2. Okay, let's see. Well, we'll start with the vector. So again, we start from this basis of vectors v1 and v2. We'll like to produce a basis of vectors which are orthogonal, and then at the end, we'll like to normalize those vectors. Okay, and then guess what? We'll apply the Gram-Schmidt procedure. So as you can see here, the procedure, W1 is the same as V1. And now we have to compute W2. So let's do it. We'll keep W1 as V1, which is 1, 1. And now W2, by the formula here, is V2, okay? So it's V2 minus, well, since in R3 the inner product space is just dot product, V2 minus V2 dot W over W1, sorry, over W1 dot W1, W1. Okay, and this will be, this is 0, 1, minus the dot product between V2 and the W1 is 1, and this guy 1 over, and here W1 squared will be nothing else than just 2. Okay. W1, which is 1, 1. So this will give us the vector negative 1/2, 1/2. Okay, great. Now the set B prime, which will consist of these vectors W1 and W2, is an orthogonal basis for R2. And now we want to normalize each vector. So we want to normalize each vector. So what we're going to do, we're going to take each vector W1 and W2, and we're going to divide it by its length. So we're going to consider these vectors, U1, which will be W1 divided by the length of W1, and this will be 1 over square root of 2, 1, 1, which is 1 over square root of 2 and 1 over square root of 2. Okay, great. Now the vector U2 will be W2 over the length of W2, and this would be 1 over square root of 2, I think, yeah, times negative 1/2 and 1/2, yeah, which will give us square root of 2. And this guy is nothing else than just negative square root of 2 over 2 and square root of 2 over 2. So these are my two vectors. Well, clearly, this implies that this basis B second prime, which will consist of these vectors U1, U2, is an orthonormal basis for R2, right? Okay, now let's see another example. Well, a little bit more complicated, 3 by 3 examples, and then we will see. So this is example number 6. So again, the same thing. We want to apply the Gram-Schmidt procedure. Okay, to the basis, and now let's consider a basis B for R3. And this basis will be given by the following. Let's pick up some vectors. Let's say 1, 1, 0, then 1, 2, 0, and 0, 1, 2. So these are my 3 vectors. There'll be some computations here. Exactly. My ultimate pleasure to do computations in the middle of the night. Anyway, let's do them. Okay, Okay, so we'll start with we would like to take again this basis of vectors of v1, v2, v3, and we'd like to transform these vectors into firstly into a basis of orthogonal vectors, and then next we will normalize that orthogonal basis. But let's do this. First, we'll start with W1. We'll keep it as V1, which is 1, 1, 0. Start with. And we continue with the following, with W2, which will be V2 minus, okay, I just have to put the dot product since we're in R3. V2 minus V2 dot W1 over W1 dot W1 W1. Okay, and now we will compute this, and this will give us the following. V2 is 1, 2, 0 minus V2 times so this guy W1 will be 2, and okay, this inner product, the dot product here, V2 W1, okay, 3 over 2 times 1, 1, 0. Okay, great. And this will produce, this will be negative 1/2, and 0. Okay. This is will be my W, will be W2, and now W3 will be, again, by the same formula, V3 minus V3 dot W1 over W1 dot W1 minus V3 dot W2 over W2 dot W2. And now let's do this. It will be 0, 1, 2 minus V3 W1. This would be 1/2, 1, 1, 0 minus minus V3 W2. This is 1/2 over, this is 1/2 times W2, negative 1/2, 1/2, 0. Okay, great. And finally, this will give us, let's write it, 0, 1, 2 minus 1/2, 1/2, 0 plus, okay, minus, in any case, now let's see, this is 0, 0, and 2. Okay. Then the set B prime, which will consist of these three vectors, W1, W2, W3, is an orthogonal basis. For R3. And now we want to normalize each vector, normalizing each vector we have. So now what we need to do, let me point out here. So this is W3, W2 is this guy, and W1 is this guy. So we want to normalize this, and we'll have the following: U1, which will be W1 divided by the length of W1, and this is 1 over square root of 2, 1, 1, 0, and this will be 1 over square root of 2, 1 over square root of 2, and 0. Okay, now we're going to do the same thing for U2 and U3. U2 will be W2 over the length of W2, which will be 1 over square root of 2, negative 1/2, 0, which will give us negative square root of 2 over 2, right? Square root of 2 over 2 and 0. Okay, great. And the last one is the following. It's 1/2 times 002, which will be nothing else than just 001. Great. And finally, I have my my basis of orthonormal vectors. Let's write them. So the set, this, which will consist of vectors U1, U2, and U3, is an orthonormal basis for R3. Okay, great. Right? It's a very simple example. And now, maybe I have one more example. Yeah, maybe I should take how to. So one more example. Example 7. And in this example 7, I want to use some integral calculus again. So again, we want to apply the Gram-Schmidt procedure to the basis. And I'm going to consider the following basis. B will consist of these functions, 1x and x squared. In fact, these are polynomials using using the inner product let's say, so these are basically monomials, they're polynomials. I'm going to PQ, this will be the integral from -1 to 1 of P of x times Q of x dx. Okay, great. So let's start with the following basis. So let us consider B. Let's start with this basis, 1x and x squared. So these will be, let's say, my vectors v1, v2, and v3, right? Okay, great. Now again, we start with W1 to be as the same as V1, which in our case is 1. And now we apply the Gram-Schmidt procedure, and now we can write W2 as V2 minus V2 W1 over the inner product between W1 and W1. Okay, this will give us V2 is X minus V2, this will be 0 over, this is 2 times 1, which will be X. So we get W2 will be the function X. Okay, great. Now we look at W3. This will be V3 minus V3 dot inner product with W1 over okay, great. And now this will give us, so V3 is X squared minus, this is the inner product between V3 and W1. Oh my goodness. So it's 2 over 3 over 2 times 1 minus the last one will be 0 over 2/3 times X. Anyway, this will give us X squared minus 1/3. And now we want to normalize this. Normalizing, we get the following. So wait, we want to normalizing this basis, which consists of these vectors, W1, W2, W3, we get the following. So again, I'm going to consider U1, which is W1 over, well, the same story. Times X, which is square root of 3 square root of 2 times X. And U3 is oh my. This will give us whatever W3 okay, I have this here. This, okay. So W3. It will be a constant. Anyway, we'll see. Times the function x squared minus 1/3. And this constant, W3 from W3. Okay, I think this should be 1 over 8 over 45, I think, if I'm not mistaken. Anyway, so this will give us 3x square root of 5 over 2 square root of 2 times 3x squared minus 1. Okay. So now we produce an orthonormal, finally, basis. Fact. That's it. Right? Let me see. Yeah. Okay, I think I'm maybe, yeah, maybe I should mention one thing, a remark. I think I'm going to stop because I want to simplify it a little bit. So we can have the following alternative. To the Gram-Schmidt procedure. And this following alternative will be the following. And let me write it in this way. So U1 will be W1 over the length of W1, which is nothing else than V1 over the length of V1. And now U2 will be W2 over the length of U2, where W2 is nothing else than just V2 minus the inner product between V2 and U1. Yeah, that's actually in simpler. Now we can write U3 as W3 over the length of W3, where W3 will be nothing else than just V3 minus V3 U1 minus the inner product between V3 and U2, and we keep going all the way to the last one. UN will be nothing else than just Wn over the length of Wn, where Wn will be Vn minus Vn U1 minus all the way to the inner product between Vn and Un minus 1, Un minus 1. Okay, that's we can write them in this way. It's basically the same thing, but yeah. So that's the Gram-Schmidt orthogonalization procedure. I think, well, let's do one more example, because I want to show you also how to solve a homogeneous system of linear equations using this. Why not? So this will be example number 8, and I think I'm going to stop after this. Okay. This example will be the following. Let's state it in this way. Find an orthonormal basis for the solution solution space of the homogeneous linear system. And now I'm going to consider the following system. S will be two equations, 4 variables, x1 plus x2 plus 7x4 is 0. And the second equation will be 2x1 plus x2 plus 2x3 plus 6x4 is 0. Right? And now what we're going to do will be the following. So by the standard procedure that you have been used by now, we write the augmented matrix associated to this system. We'll perform elementary raw operations, right? We'll try to write to reduce it. And then clearly this will have infinitely many solutions. You will find a basis. You'll see that a basis for the set of solutions for this system will consist of two vectors. And then guess what? For those two vectors, we'll apply the Gram-Schmidt orthonormalization procedure. So that's the story, and I will just glance through this. Let's see. Let me just give you the sketch. And now I'll leave the details to you. Okay, so let's write the augmented matrix. For S, which is the following, which is 1, 1, 0, 7, 0, 2, 1, 2, 6, 0, and perform elementary row operations and A reduces to let's see, I think I've done it somewhere here. Let me see. This example, so that I don't have to do all the computations. Okay. So this will be 1, 0, 2, negative 1, 0, 0, 1, negative 2, 8, 8, 0, okay. And now, if we let x3 to be S and x4 to be T, with S and T real numbers, then we can write this solution system as the following: x1, x2, x3, x4 as, this will give us negative 2s plus t, 2s minus 8t, s and t, or you can write this as s, negative 2, 2, 1, 0, plus t, 1, negative 8, 0, 1. And clearly, if you look at these two, the set of solutions is spanned by these two, right? So one basis for the solution space is the following. Okay, and now I'll leave it to you to find So I'll leave it to you as an exercise. Find an orthonormal basis, let's say P prime, which will consist of these vectors U1, U2, using the Gram-Schmidt procedure. Okay, I'll leave it to you as an exercise. Okay, guys, I think I'm going to stop here. Thank you very much. And next, we will talk about, again, orthogonal diagonalization of matrices.